It's a pleasure for me to introduce Dr. Audrey Grockowiak. She's a research faculty, visiting research faculty at the High Magnetic Field Laboratory in Tallahassee, Florida. And just a few words about how you should enjoy this talk. Dr. Grockowiak, she's an expert on things that not many people in the world are expert on. So we have many people that do high pressure studies in materials. We have quite a bit of people that do high magnetic field studies. Some people that do low temperature, but not many people that do the three things simultaneously. So she's going to tell us today about some beautiful fermiology studies in the high TC cuprates. So I hope you enjoy her talk. Thanks for coming and being here.
Thanks, Paula. So again, thank you very much for the invitation. It's a pleasure for me to be here today to spend part of the week with you guys. I'd like to start by thanking all of our funding agencies. So for the MagLab, we are funded by the National Science Foundation and the state of Florida, and our research is funded by the Department of Energy. And I would like to thank also EastEx for sponsoring my travel here. I would like also to thank my collaborators, co-workers, so William Coniglio and Stan Tozer. So the results I'm going to show you today are actually the product of a teamwork. So nothing could be done on my own or just one person of that team, so it's really a big team effort. So William Coniglio here on the left, he's one of the world experts for electronics in pulse field, but also DC field, and he's done all the developments that I'm going to show you today. And Stan Tozer, he's also a world expert for designing pressure cells that work in high magnetic fields, and he's worked for the past 30 years, I guess, working on those cells. And I actually make those cells work, so that's my big contribution to that project. This particular work on the cuprates and YBCO in particular was started by discussions with a group of Louis Taifa in Canada at the University of Sherbrooke, so I thank their collaborations. And the samples come from the University of British Columbia, so they're the most famous growers for that sample, the type of sample. And we have done a lot of work in pulse field in Dresden, so I'd like to thank also our user support over there, Tobias Foster and Eric Gernhardt. So I would like to start by reminding you of the unconventional superconductors. So unconventional superconductors cannot be described by the standard DCS theory. And some families, so cuprates, but also heavy fermions, serum-based compounds, uranium compounds, or also organic superconductors, actually all fall on the same phase diagram, so the so-called now universal phase diagram for unconventional superconductors. So in this phase diagram, where I show temperature versus a tuning parameter that can be either doping or pressure for that compound, all those unconventional superconductors share similar characteristics. So at low tuning parameter, low doping or pressure, they start by an insulating phase, and most of them are anti-ferromagnetic. And then as you increase the doping or the pressure, they become more metallic, so either with a strange metal phase or at higher doping fermi-liquid, so standard metal. They develop a superconducting dome, one or several domes, and most often, so this dome or several domes are stabilized around the quantum critical point or several quantum critical points, and the reason for that is still unknown and subject of investigation. So the object of our work is to look at those unconventional superconductors and try to see, by pressure actually, and looking at high magnetic field, what can we learn from those systems. I'm frozen. There we go, okay. So what we look at with those compounds is actually the Fermi surface of those compounds and how the Fermi surface evolves with either doping or pressure, in our case pressure. And we measure the Fermi surface by looking at quantum oscillations, and we do for that contactless transports. And we use pressure cells. So this is a picture of our pressure cells. And the phase diagram that we work in is pressures up to 25 GPa, helium-3 temperatures, and static fields up to 45 Tesla, or pulse magnetic fields up to 85 Tesla or something interesting. So here is the outline for my talk today. I'm going to give you an introduction to quantum oscillations and remind you what the Fermi Surface is and how we measure it. I'll spend quite some time on the various experimental techniques that actually enable the science for us. I'll remind you what the high TCs are in particular to Cup rates, and I'll finish with our result of our work. So let's start with quantum oscillations. So just to remind you briefly, metals have a Fermi surface, and basically the Fermi surface is the highest energy level that's available for the various charge carriers in one given metal. So now if you place that sample inside the magnetic field, so the various energy levels are quantized into Landau levels or tubes along the field, and each level is given or described by this equation. So each energy level is proportional to the field, also the effective mass of the carriers, and those are quantized. So you understand that when you increase the magnetic field, you increase the energy of each level. So what happens when you increase the field so much that the energy becomes greater than the Fermi energy, all the carriers that are located onto that energy level fall back onto the next available authorized energy level. And this is what is shown here in this animation. So here we show the occupation as a function of the energies. And when the field is increased, the energy also increases, and the charge carriers fall back onto the next available energy level. So now, any physical quantity that depends onto the density of states, as you increase the field, will show oscillations as a function of magnetic fields. This is what is shown here. So those oscillations are called either the Haas-von-Alphen, DHVA for thermodynamic properties, so magnetization, torque, or specific heat, or Shubnikov-de-Haas for transport properties like resistivity or Hall effect. But those are two different names for the same physical effect for quantum oscillations. So how can we characterize these quantum oscillations? The oscillations are periodic in 1 over the magnetic field. And the frequency of the oscillations is characterized by the Onsager relation. And this Onsager relation links the frequency to the area of the Fermi surface that's mapped. So for example, if you take a look at this standard Fermi surface, you have here one area, external area of the Fermi surface, but you can also have here a next that will give you a second frequency that will also give you the area of that neck. Then what can we do? So by rotating the sample with respect to the field, we can probe all of the various areas of that Fermi surface. So by rotating the field, we have all the shape of the Fermi surface in all directions. This is at base temperature, and by increasing the temperature, so by looking at the temperature dependence of the amplitude of those oscillations, we can actually fit. So let me go back. So first, we look at those quantum oscillations. By taking the Fourier transform, we get one peak or several peaks if there are several frequencies. And now, the amplitude of the peak actually depends on the temperature. So if we plot the amplitude as a function of temperature, we can fit that curve with a Lifshitz-Kozelich equation. And this is a well-known equation for quantum oscillations. And that equation has only one free parameter, which gives you the effective mass of the quasi-particle. So by doing a temperature dependence measurement of those quantum oscillations, we can access the effective mass of the quasi-particle in the sample. So those are the two main things that we get from quantum oscillation measurements: the area of the Fermi surface and also the effective mass of the quasi-particles. So the trick with those measurements, so they're not easy. So you need really high purity crystals, because any type of disorder will prevent the electrons to go into cyclotron motion and prevent any oscillations. You need very low temperatures. The higher the field, the better the oscillations. You need to go oftentimes to high field facilities. And for pressure measurements, you need hydrostatic conditions, and I'll talk more about that later. So for us, high pressure is actually a clean way to tune the doping, or actually a clean way to not introduce too much data. Yes.
Can you rotate in 360 degrees or magnetic field by a vectorial magnet?
So we don't rotate the magnet, we rotate the sample of the field.
Okay, and you can rotate in 360.
So we can in principle, but then you have other constraints. So for example, if you have wires for your measurement, you have the length of wires. So usually we rotate only one axis, and we rotate like 45 degrees or 90 degrees. But in principle, yes, if your sample is small enough, or if your pressure cell is small enough, you could rotate. But then you have other constraints. So now, how do we make those measurements? So I'll start with pressure cells, and pressure cells they're typically very big, and the main criteria for pressure cells, or actually for diamond anvil cells, so you have two diamond anvils here. For hydrostatic condition, we need a pressure transmitting medium, so most often a liquid, and the liquid is held in between the two anvils by a gasket. So to reach the highest pressures possible, we need the two anvils to be perfectly parallel together. So most pressure cells will have various aligning processes, various screws, and those pressure cells can be pretty big. But for the magnets, actually, the sample space is rather limited. So we have about 32 millimeters for static field, in which we have to fit absolutely everything. So we have to fit the probe, we have to fit the cryostats, and we have to fit the pressure cell. So Stan Tozer, my mentor, developed a pressure cell based on the turnbuckle principle. So this is a turnbuckle, and those devices are generally used to put wires in tensions or cables in tensions. And in that case, he used this principle to actually put two devices under pressure. So he developed those two cups in which we put the diamond anvils. And if you have a really good machinist, you can ensure a very good parallelism for your diamonds. So those two cups have opposite threadings. One has a right-hand threading and one has a left-hand threading. You can place those two cups inside the body, here shown in green, and the body has a matching threading. And by rotating the body, you bring together the two angles, and this is how you generate and retain the pressure. So this is a very simple design. It's self-aligning, you don't need to have extra screws or anything. And you can design them to be pretty small and to fit inside the magnets for us. And it has several designs, so either metallic ones, one here with a large aperture for optical measurement, and some made out of plastic to do pulse magnetic field measurements to avoid any heating or vibration due to the strong gradients in field. So we can rotate them at helium-3 temperatures. We can go up to almost 12 GPa with the plastic ones and up to 25 GPa with the metallic ones. We use different pressure media for different purposes, because some pressure media can react with the sample, so we have to be careful about that. We have to be careful also about hydrostatic levels. Not all of them are really hydrostatic. Usually we do not make resistance as a function of temperature measurements, because the pressure does not stay constant as you lower the temperature. So there are many publications out there of resistivity versus temperature in pressure cells, and they never actually comment on the change of pressure as a function of temperature, but this is the reason why we don't do that kind of measurement. And the last point that's interesting for those pressure cells is that for the plastic ones, since they're made out of plastic, they're transparent for X-ray. So this allows full rotation of a sample in a beam, which can be usually difficult for X-rays. This is what a typical setting looks like. So what you see here, this rim here is actually the cullet of the diamond, the tip of the diamond. The dimension here would be 500 microns. This mostly transparent part here is the gasket to hold the pressure medium. And in our case, we use non-metallic gaskets, so mixture of diamond powder and epoxy. The sample is located here in the center, and this is the pickup coil that we use to make the measurements, and I'll talk about this later. And we measured pressure by looking at the fluorescence of ruby. So I place here several rubies inside the sample chamber. So how do we make those measurements? So we look at, we use a tunnel diode oscillation. So it's basically RF tank circuit or RLC circuits. And this is actually what we learned in the high school in France. So RLC circuit has a resonant frequency. And in our case, the inductor, the L, is that coil here in which I place the sample. So the inductor is inside the pressure chamber, or the sample chamber. And when I place the sample inside the inductor, I change the resonant frequency. So now when the sample also changes properties, when it becomes superconducting or when it goes through magnetic transition, the resonant frequency also changes. So this is what we measure. We measure shifts in frequency. And it's a very convenient method because it's a contactless method. And like think about here the dimensions of that sample. So here it's typically 100 micron diameter sample for 20-30 microns thick. So try putting good low contact resistance contact on that small sample. So for us it's a big advantage to not have a contact on the sample. So what do we measure with that technique? We can measure so skin depth for metal, penetration depth for superconductors, or also magnetization for insulators. And what else? So it couples very well with the high pressure technology. So also for samples that are can react also with either epoxy or things like that. The fact that we don't have contact makes it very easy. We have also other sensitive samples, either radioactive or air sensitive samples. So I work a lot with lithium. Lithium is very difficult to work with, but if we work in a glove box, just dropping a sample in the coil makes it very easy. So overall, it's a very friendly method, but the major drawback is that it's not a diagnostics tool. So for example, when you look at a superconductor and if you make a transport measurement, you know you got into a superconducting region when you go to a zero resistance state. So in our case, for tunnel diode oscillation, we just see a shift in frequency. So if we want to make this kind of measurement, we need to have some prior knowledge of the sample to know where to expect a transition, for example, and then follow the trend and the pressure. So doing transport measurement in high pressure is also doable. And here is one effort that we've been working on for 2 or 3 years now. And it's coupling focused ion beam technology with diamond anvil cell. So it's a large collaboration that was started by people at Los Alamos. And it combines the expertise of focused ion beam, pulsed field electronics, and high pressure. So here you see the picture of the cunettes of our diamond anvil, again 500 microns in diameter. And what our colleague at the pulsed field lab in Dresden does, so he takes a sample, so this is the sample here, this clear part that you see in the center of the cunette, and blown up, this is the sample, the whole white region. And with focused ion beam, he designs a device, so he calls that a device. And he creates also well-defined contacts on the sample. So the advantage is that we have well-defined contact geometry. Here you can see that we measure several axes of the same crystal. So here the A-axis and the B-axis, but you can also measure simultaneously transport and Hall effects in the sample. And looking at this picture, we see that the leads go on the anvil instead of going through the anvil, so through the gasket. So when we apply the pressure, the fact that we have a gasket on top actually does not destroy those leads, so it makes it really robust when we apply the pressure. So it's for me, it's the future for high pressure transport. So now going to high TC superconductors. So I showed earlier this universal phase diagram for a strongly electronic system, strongly correlated system. So the cuprates are a family that has this phase diagram. So they share common features, it's a whole family. They can be either electron doped or hole doped. And so YBCO is one hole doped cuprate. So So the cuprates have copper oxygen planes separated by charged reservoirs, and depending on what you put in those charged reservoirs, you get either neutron dot or a whole dot system. YBCO has the extra complication that it has charge density waves happening to it. So this is a current phase diagram of YBCO, so temperature versus doping. Most of the work on YBCO has been done with doping and not with pressure. So you see here in gray the superconducting dome with a very peculiar shape of this shoulder here that intrigued the scientists for a good 15 years, and then eventually they discovered that there is a 2D charge density wave that's competing or collaborating, it's still debated, with the superconducting dome. So this 2D charge holder is present at zero magnetic field, and that's an important point. And more recently, it was found that there is a second charge holder, this time 3D, that shares some characteristic with the 2D, but this one develops only at high magnetic fields, so above 18 Tesla, and that's an important point here in the story. So this is for the phase diagram of YBCO, and for the current picture of the Fermi surface of YBCO. So right now, for the underdoped side, it's believed that there are small Fermi pockets, and as you go to the underdoped to the overdoped side, you develop a large Fermi surface. So that was observed somehow with RPS. But the problem is that you cannot produce samples that are overdoped. So the maximum doping that you can get is actually here optimal doping. So all of those measurements were actually done on analogous samples. So basically the thallium doped cuprate, depending on the amount of charge carriers that are in the copper oxygen plane, people decided that it was a good analog to the overdoped YBCO. So this picture actually comes from a completely different sample. So currently there are no direct measurements on the Fermi surface of YBCO on the overdoped side. So I show here again a different picture of the phase diagram of YBCO. So if we want to measure quantum oscillations, basically we have samples available up to here, to optimal doping. So those symbols here are the various dopings where quantum oscillations have been measured using transport measurements, for example. And so to measure quantum oscillations, you have to be into the normal state of the sample. So you have to somehow suppress the superconductivity. So to suppress the superconductivity, we have to apply a high magnetic field. So this is here the estimated dome of a critical field. And so to measure those samples, you can either use 45 Tesla in Tallahassee and you have access to this range of doping, or go to Los Alamos and use the 100 Tesla magnet and you can access this region. But to go to a higher field is really difficult, and actually the estimate is that to go to optimal doping, you have to reach beyond 150 Tesla. So right now it does not exist, or it's really complicated with different magnets. So our idea was to, not by tuning the pressure, not by tuning the doping, but by increasing the pressure and therefore tuning the doping, look at this overdoped side and try to drive the sample into the overdoped side. So we start with an underdoped sample, so somewhere in this low region of the charge density wave. We want to look at this evolution of the charge holder and superconductivity with increasing pressure, and at some point, to high enough pressures, look at this part of the phase diagram. And the important point that I want to make here is that I don't make a direct comparison between pressure and dopings. So pressure will change the doping, but will change also other things. So we're basically looking at a new axis of the phase diagram, but hoping to take a look at what's going on here. So for our results, so those are our first data that we collected in pulsed magnetic field in Dresden, so 70 Tesla magnet, and that was done at 8 kilobar and helium-3 temperatures. And what we see here is I plot the TDO frequency that we measure as a function of magnetic field, so up to 65 Tesla here. And you see two curves here, one purple and one green. One is for the upsweep of the pulse, and one is for the downsweep of the pulse. And one thing that's really important for us is that those two curves overlap perfectly. And we see that by those oscillations here that have the same amplitude. So the fact that those two curves overlap perfectly means that by using completely plastic technology of cryostats and pressure cells, we do not generate any heat during the pulse. And for us, it's really important.
And the small shift.
It's very tiny, and if you compare with other experiments, actually other people working in pulse field will show you only the upsweep. So if somebody does not show you the downsweep, it means that there is heating and you don't see the oscillations, or you have like a straight curve that does not fall back to itself. So this small shift is actually not that much.
Say like there is very no heating.
There is actually no heating. There is no heating, and for us the argument that there is no heating is that the amplitude of the quantum oscillation is the same. So if there was some heating, the amplitude would drop. So we see here those beautiful quantum oscillations that appear. This transition here, we attribute it to the superconducting to normal transition. So that's the HC2. And so what we do for analysis is that we take the part that shows oscillation, we plot it here with a background subtraction, and then we take the Fourier transform of that part, and this is what we show here. So one main peak here. And
So what frequency that's...
so that would be around
500 Tesla?
close to 600 Tesla. Yeah. I don't put here. Yeah, I forgot to put it here, but yeah, that's that around 600 Tesla.
And I know you are now going into a third axis, but can you guide us into like what field or what part of the phase diagram you would be? Because presumably you will have some optimization of superconductivity. Are you beyond on the right side of the dome or on the left side of the dome?
So I'll show that later, but this is like a rather small pressure, so that's like 8 kilobar. So right now we're still on the underdome side and like still on the below the optimal part of the charge order.
And how does that frequency compares with the one with doping?
It's actually very close to the one with doping, so and I'll show that later. So this is one pulse at helium-free temperatures, and we repeated that. Actually, we went back to Tallahassee to work in 45 Tesla hybrids, and we did that measurement for various pressures, from ambient pressure up to almost 70 kilobar or 7 GPa. So again, I got here the TDO frequency as a function of field. For those increasing pressures, we see here again the HC2 critical field, and this critical field increases a lot with pressure, but in a non-linear way. So here around 46 kilobar, it decreases again before increasing again. So there is something non-monotonous here happening. And then by basically 70 kilobar, we literally run out of field in the 45 Tesla magnet. So 45 Tesla is no longer enough to see quantum oscillations and continue our study. So we have to go back to pulse magnet to look at the next pressure range, which is really different. And so this is what we did recently. So that was our first run in Dresden in the 85 Tesla magnet. Usually we run the 70 Tesla magnet, but we managed to get access to the duplex magnet, 85 Tesla. And so for a pulse magnet, to get to those really high fields, you need to dump a huge amount of current in the magnet. So it means that you warm up the magnet pretty fast. It means that you need to wait for the magnet to cool down in between two pulses. So for that magnet, we have to wait 5 hours in between two pulses, which means that at best you get like 3 pulses per day, which means that you have to optimize absolutely your experiment. So this is a picture of the probe that we developed and rebuilt in Dresden, and we can actually see 3 pressure cells here. So one on top here on the rotator to rotate in field with the laser to measure the pressure. A second one here also on the rotator, and the third one here on the fixed axis. So we can do 3 simultaneous high pressure measurements in pulse field. And those are our initial data in 85 Tesla magnets, so here up to 75 Tesla. And we went as high as 75 kilobar. It's really difficult to make those pressure cells go to higher pressures. So what we do for all of those pressures and for each of these, for all of those pressures is actually to do a temperature dependence study to get an effective mass. So we do that for all the pressures. And this is one typical example that we did in Tallahassee, 45 Tesla, and at about 48 kilobar. So this is for one pressure. Here I show the TDR frequency as a function of field for increasing temperatures. And we see that for increasing temperatures, the quantum oscillation amplitude decreases and dies basically by 7 or 8 Kelvin. So by taking the Fourier transform amplitude and by plotting this amplitude as a function of temperature, we get this curve, which we fit with the Lifshitz-Kozefic equation. And this gives us the effective mass of the carriers. And we get about 1.9 electron mass per seconds. And now plotting all of our various data in this plot. So I plot here the TC as a function of pressure, so I can measure the TC in our PPMS. So for increasing pressures, there is an anomaly here. The critical field measured in our hybrid magnet. So again, there is a region here where it's non-monotonic. The frequency of the quantum oscillations again shows something happening in that region of the pressure. And again for the effective mass. So all of those quantities show a non-monotonous behavior in the pressure range of 30 to 50, 55 kilobar. And we attribute that to the effective pressure to the charge density wave. And so again, so by applying pressure, we change the doping, but not only, we change also other things like this. So if we compare with the whole doping, so at ambient pressure we were here, about here, and by tuning the pressure, and if we compare with the critical field, we go to about here, this doping with 7 GPa. So we're still below optimal doping, and the next question is, how far in pressure do we have to go to the overdose side, or what it is to be the overdose side? And
Sorry.
yes.
So how about the mass? Have you plotted the inverse mass to see if it follows the same trend than
We have not plotted that yet. I mean, actually, we have a lot more data than that, and we need to make more. We need to make more analysis to get all of the effective masses of all of our various models.
Because it would be interesting to see if
Yes,
it's
exactly.
actually following the divergence
Exactly,
right
yeah.
at the same spot.
Yeah. So.
In the doping.
So we have many runs. We are still trying to analyze the run from Dresden from last November, so that's about a year ago now, and it's tricky. And so actually, we need actually those data in pulse field because we have more oscillations, and that will give us a better resolution on the frequency and also on the effective mass after. So it's a lot of work, and we are understaffed right now. So it's work in progress. It's work in progress. But yes, that's something that we need to understand.
Why is that the effective mass increases beyond 1? I mean, what is the meaning of that? Normally it should be less than 1.
Not really, it's a heavy Fermi.
Okay.
So it's more on the heavy Fermi side, or like strongly correlated
So
systems.
that's what you expect.
Yeah, this is what is observed already for the samples tuned with doping. So there is nothing surprising for us here. So for the sample that's here, the effective mass is also of the order of 1.9. So we are in a really good agreement with what's been done with doping.
And how can you correlate directly your results that resembles doping? It could be due to something else, right?
I'm sorry?
We're saying that by putting pressure, you are increasing the doping.
So I'm saying that this is one thing that we change, but I also insist that pressure changes other things that we look basically at the third axis.
Right.
So yeah, pressure does change the doping, but you change different things, and I'll discuss that after.
Okay.
And you only observe one frequency.
We observe only one frequency for the cancer. So So our main focus was to apply some pressure and see if we could get to that region of the phase diagram, so to the high pressure overload side. And this is what we did repeatedly. So on pressure cells at 20 GPa and beyond. So the first comment I would like to make is that 20 GPa is way beyond the hydrostatic limit of any known pressure medium. So I was using methanol ethanol, and methanol ethanol is no longer hydrostatic from 10 GPa and above. So this is a technical point, but usually quantum oscillations are destroyed by non-hydrostatic conditions. So the fact that we did observe quantum oscillations was just exceptional in itself at that such a high pressure. And again, 20 GPa, it's really difficult to get with leads that have to go through a gasket, and there's a very high failure rate for that type of pressure range. So that was a technical comment here. But here I plot the background subtracted data for 4 different pressure cells at different pressures ranging from 188 kilobar up to 250 kilobar. And we see again the critical field transition here and the quantum oscillations. So not all of them show such strong quantum oscillations, but at least the 188 kilobar shows very strong quantum oscillations. So here, what's really important is that we have the critical field that's of the order of 29 Tesla. And if you remember, at 70 kilobar, the critical field was of the order of 44 Tesla. So for me, this is the main argument that we have pushed the sample to the other side of the dome, other side of the superconducting dome. So we are on the other side of the superconducting dome. We have quantum oscillations, and the frequency is not much different than that observed also on the underdome side, so of the order of 700 Tesla compared with 600 Tesla on the underdome side. So this is, if we plot this data in that phase diagram again, we are somewhere here on the underdome side of the superconducting dome. So how does that compare with the initial picture that I showed you earlier with the large Fermi surface that was obtained with the thallium doped crate? Those are the results obtained by different groups on that compound by doing either torque or transport measurements. And basically what they get is one frequency of the order of 18 kilotesla, and effective masses of the order of 4.1 electron mass. So this is completely different from our result of 700 Tesla. So this is also for me main argument that pressure and chemical doping are doing things that are completely different. And this is, that's one way of looking at it, but also this is a very active area of research. So what does pressure do to cuprates? And
sorry, but you can't really compare those numbers, right? I mean, they are different systems anyway. So thallium and YBCO. So of course, like YBCO needed to be done.
Mm-hmm.
So, but if there is no, I don't know if there is a reason to think that the pockets would have exactly the same size. Like maybe phenomenologically that it is some Fermi liquid kind of or just a spherical pocket would be probably something that you could say they are similar Fermi surfaces, but in terms of size that shouldn't be the case, right?
I totally agree. So and you know how the story was written for the cuprates. So people have had arguments that thallium should be the analog overdoped. So people have pushed to have this picture of a large Fermi surface versus small Fermi pockets for YBCO, and they pushed for this reconstruction of the Fermi surface across the superconducting dome. But yes, for me, I don't quite understand, I don't fully understand the argument why thallium should absolutely be the reference for overdoped YBCO. So, but depending on the community, you cannot say that out. So.
But the effective mass is changing a different.
The effective mass is very different compared to the different systems. Yes. So for that compound thallium, the effective mass is 4.1, and what we get is of the order of 1, 2 yeah, the results are completely different. So it's either you say that their interpretation that thallium is the overdose analog of YBCO is wrong, or we say that there is something happening actually with pressure that can also give us different results. And so pressure in the cuprate or on the cuprates is actually investigated quite a lot now. And so there is one group led by Mathieu Le Tacon, so he is a group leader at Max Planck, in Karlsruhe Institute of Technology. And so he is a X-ray person, and he's worked a lot on the cuprates. So he has done recently two bodies of work that actually helped me a lot interpreting my results. So the first one was applying hydrostatic pressure on YBCO. So he looked at this one doping, so 6.6, which is very close to my initial doping. And he did high pressure inelastic X-ray scattering to look at the charge density wave of YBCO, so the 2D one. And what he saw is that that charge order was suppressed by 10 kilobar in that compound. So then what he did is that he recalculated, so 10 kilobar, he said that by applying 10 kilobar on that compound, I changed the doping by 0.15. And then he took one sample with that doping, since 6.75. He looked at inelastic X-ray scattering at ambient pressure, and he actually found that the charge order was still present in that one. So that's one main argument saying that pressure and doping have very different effects. So in one case, pressure kills the charge order, and in the other case, doping actually still sustains the charge density. My main problem with that work is that he stopped at 10 kilobar, so we don't know what happens at 20 GPa, for example, if there is still a charge order present there or something. And those are only zero magnetic field data. And if you remember from the phase diagram that I showed earlier, there are two charge orders. So another one develops at high field, at 18 Tesla. So maybe there is another one that's still present at pressure. And then,
sorry,
yeah.
I have a question because I'm not from this field, but can you tell us a bit more about 2D and 3D charge order? What does that mean? If it is easy to explain.
So I'm not extremely familiar with the charge orders, but some of them can develop in the plan, and some of them have a three-dimensional component.
Okay, so they're actually dimensional.
Yeah, so those are dimensional. So those are basically electronic modulation about the lattice modulation of the sample. And so there is a 2D one that's literally two-dimensional, that has two vectors. And there is a 3D one that develops on top of the 2D one when you apply a magnetic field. Why that is, people are still wondering. But those two, the 2D one and the 3D one, are commensurate. So in the 2D plane, they actually have similar dimensions.
So the 2D one is easy to see in the cuprates, but the 3D one is not so easy to see, is it?
It is easy, but if you apply a magnetic field.
Okay.
Because you need a magnetic field to trigger it.
Okay.
And since that study does not have magnetic field, it does not look at the pressure effect on the 3D one.
Okay.
But you could say also the same for the 2D one, right? When you apply field, you are revealing the nature of the 3D charge density waves. So what you're basically probing with quantum oscillation is the reconstructed Fermi surface by the 3D charge density wave pocket, right?
Yes. Yes. So then Mathieu Le Tacon continued his pressure work, and he teamed up with the group of Andy McKenzie, so at the Max Planck in Dresden, and McKenzie and his group, so Clifford Higgs, he's actually an expert for uniaxial compression. And so what they did is that they developed a uniaxial setup to look at, again, inelastic X-ray scattering. So they developed a specific setup to be used inside a sequentron, so in Grenoble. And they applied uniaxial pressure along certain axes of YBCO. And this is where it becomes really interesting. So he found that upon uniaxial compression along one axis, the a-axis, you could still see the 2D charge order, but then by increasing the compression to the order of about 1%, you could recreate the 3D charge order, which was observed before only under high field. So here we have the question, and still being investigated between the strain and also high field. And one way that I look at my data is that maybe by applying hydrostatic pressure, at some point I get to a similar compression along the a-axis that also recreates a 3D charge order, which will also explain the quantum oscillations from that charge order and not to something different than charge order. So this is where I am right now in our work. So again, we're looking at a new axis of the phase diagram with pressure. So we're one of the first team to look at the pressure effect on CDW and on quantum oscillations in YBCO. So we believe that by tuning the pressure, we are on the overdose side of YBCO, and that study is actually the first study of quantum oscillation and looking at the Fermi surface of the overdose YBCO. And we have actually more work to do. So we want to look at the Hall effect under pressure for YBCO by doing a FIB with our collector helm, and also measure ourselves the thallium dot compound to see if we can also recreate the same results. So that's it. Thank you for your attention.
You mentioned just brief at the end that somebody was applying pressure along the a-axis.
Yeah.
Have they done along just the c-axis to see the effects?
So they have done the three axes, so A, B, and C. So they have published only the results on the a-axis, but in I think one of the conferences, I think March meeting, Le Taco said that by applying along the b-axis, he does not recreate the charge order. So it's really
c-axis?
not the b-axis. And along the c-axis, nothing much happens. I mean, we just like bring closer together the oxygen in the charge reservoir to the copper oxygen place. You just increase the doping, but you don't change anything about the charge order.
The TC
so it's
increases.
The TC increases a little bit.
And I've seen some information about people saying that YBCO has some insulating regions and superconductive regions coexisting. That's also other ideas I have heard about that. Can you comment on that?
No,
No?
I haven't heard of that, so I cannot comment on that. But let's say if it was the case, I'm not sure if we could measure quantum oscillations with a really homogeneous sample.
It's not really insulating, but just nano domains of charge density wave where they observe. Audrey, can you comment on the comparison of the HC2s for the doping plane and the pressure plane? Because from that no, the one you, so can you show the
That one?
Yeah, that one. Because I don't know if they are comparable, because I see that in the when you compare it in the doping axis, they are pretty comparable, HC2 and TC, but here they're pretty different. So can you comment on that, or is that the case, or?
I'm not quite sure I understand.
Because when you plot HC2, so it's almost 1-to-1, so there. So
Yeah.
TC and HC2, so it's if it's around 50, at least in the underdome area. So if TC is 50 Kelvin, HC2 is about 50 Tesla or 60 Tesla in this doping plane.
But that would be a very small region, right? Because here the critical field decreases a lot.
Sure.
So that's true just for like that point here.
But at least for the pressure, they are very, very different, actually.
So-
Almost double or something like that.
Yeah, so here, so for this one, doping, if we have about, let's say, 50 Tesla, it's about 50 Kelvin. And going back to our phase diagram. So yeah, we start here. So where is the critical field?
I see.
So here we are at 28, 29 Tesla for the critical field and 65 Kelvin for the TC. So here the TC is 65 Kelvin. If we go back to
This is just because of the region of the phase.
I think so.
So when you start
65
with,
Tesla is about
I see.
there-ish.
I see.
So
They are.
I think here we go back to the same comparison factor 2.
Any other question?
I have a question. So this IBCO, do they have to be monocrystals?
Yes.
So okay. So now how I don't know much about, because I know for the solid state preparation you can control very easily the oxygen content, but could you tell me how, or maybe how to do it on a monocrystal?
That's a question for you.
For now, yeah. Is it easy?
It's not that easy actually. So Audrey is getting her sample from the only group in the world that can actually grow a good YBCO crystals.
Okay.
There are more groups now.
There are more?
There are more groups.
Oh
now.
wow, okay,
Yeah.
I missed
But-
that.
Yeah.
So yeah, in University of British Columbia, there was this guy who became rich by selling houses. So he put all his money into preparation of YBCO, and that's why he became not the only one, but the second to
So now there are
actually be
more
able to
groups
grow
doing
good
it, yeah.
YBCO crystals. So it's not easy to have a good to control the oxygen stoichiometry,
Yeah,
but
yeah.
they manage it somehow.
Okay.
And what's really difficult in that one compared to YBCO 1, 2, 3 is that the oxygen in the charged reservoir, not in the plane, but in between the planes, they form chains.
Yeah.
And the organization of those chains can actually change the TC amount of the sample. And this is like temperature dependent. So if you put your sample a little bit in the oven at some temperature, you can completely reorganize the oxygen chains and get a completely different sample.
Yeah.
So it's not trivial at all.
Yeah.
But yeah, so you were saying that UBC was the traditional grower for the samples for like the longest time. Bernard Keimer in Germany, somewhere in Germany, I don't remember the university, grows also really good crystals. So Suchitra Neal, so at Los Alamos in Cambridge, they're using these crystals now. And Tony Carrington also, he's at Bristol. He had a student that was also very successful with growing good samples. So they're opening up the field to other sample growers, because it's true that for the longest time it was believed that any other sample that didn't come from a UBC was trash. But now people are
Because
evolving.
those samples were the only one that showed quantum oscillations
Yes.
in YBCO.
True. But now like those samples from the other groups also show really robust quantum oscillations. So,
Yeah. Okay. Thank you.
Any other question? Okay, thank you.
thank you.
Encárgate, entonces vas a ayudar.
Sí, claro que sí. No, son nanolíneas de la Universidad de Canadá, que están de orden de 10 nanolíneas. Y pues no son aislantes técnicamente, pero la universidad tiende a volverlos naturales más aislantes porque ahora son en la superficie de Fermi. Pero no gapean completamente la superficie de Fermi, entonces técnicamente no son completamente aislados, pero sí hacen que la fuerza menos letal.
Los caminos, pero, o sea, a ver, que hablaban que en el protagonismo,
Sí, son rotativo igual. O sea, la presión igual va a estar encima, está solo en
Sí, en la zona antiferromagnética.
más alto que los
Porque en la zona antiferromagnética sí, no.
Pero, o sea, ¿cómo los depositamos?
Porque
Ah,
si
en la
es
zona
superconductor
es un
son los
aislante,
blancos.
No, que se ve bien.
un aislante antiferromagnético. Los muy bajos es aislante.
superconductor.
Lo que tiene es lo que tiene
Pero
es un
que
target,
pero
como
como
un
lo
target, entonces de ahí saca átomos
En dos dimensiones.
Sí.
Sí.
Y el resto aislante.
con
No.
argón. Para que
Pues, o sea, son sándwiches de cosas, de planos que son
Yo leí
aislantes.
una vez un Pepe que decía algo así. Ah, pero tú dices que sí.
Se conducen los planos.
Ah, eso sí.
Entonces, y ese camino lo tiene que ser átomo por átomo.
Pero
Yo leí
lo
lo
que
demás.
pasa es que esa muestra
Entonces eso sí está bien.
seguro duraron haciendo un año.
Thank you very much.
Thanks for questions.
O sea, es cuando uno escribe, el trabajo se va y queda uno frito.
Yeah, but it's very complicated for you.
Yes, la
Just
misma.
because it's a mess.
Sí, pues los profesores he visto, mi hermano también tiene
The experiments are
And to understand.
the understanding, I think, the results are what they are.
O sea, no se inclina, pero además se sube y se baja.
The square from
Se te
high
puede
pressure
trabajar
X-ray is
para.
helping us a lot to understand what so we're getting.
If you can do high pressure X-ray with magnetic field,
Eso sería como que
Pero
se metálico.
Pero para convencer a la universidad a comprar.
No me acuerdo cómo fue.
Porque sí se puede hacer like synchronous, o sea, digamos que sea como diferentes, o sea, que no sea con la Austrian measurements.
Sí, voy a preguntarle a mi esposo que vio cómo le subieron el agua. Y porque se mandó otra foto que es de más detalle.
Sí,
Ah,
pues
pero
no
es
es
mecánica.
Pues creo que
Es mecánica,
Y
Para
esto
subir.
necesita ser
Sí, porque mira, se inclina.
Sí, este sí es mecánico.
Exacto, este le da una vuelta.
Pero para subir.
Y para acá no sé, tengo que
O sea, debe ser
mira que tiene que ser eléctrico. No, no es eléctrico. De pronto, sí, no sé.
quizás hidráulica.
Sí,
Para que sea más suave.
igual.
De pronto es hidráulico, no sé, pero voy a preguntar a mi marido que yo
Como en el que hacen para esto, actually she stayed to get just like se levanta y integrates for a long time.
sí, sí, hay cámaras que
that's it.
So that would be something to look at.
Chao.
Okay, thank you.
Good
Thank you very much.
Teacher.
Les gusta llover. Yo nunca traigo mi sombrilla.
It's raining like that. Exactly. It is surprising that by applying the actual pressure on the third axis, it's relaxation.
tal como